Thank you all for being here. My name is Dr. Julio Friedmann. I'm a senior research scholar at Columbia University, and we are here today to talk about CO2 removal. Thank you again for your attendance, and thanks to ICEF Innovation for a Cool Earth Forum for pulling together this event in these extraordinary times. As you know, the times we live in are difficult and unprecedented, and climate change has made those more difficult and reflect how dramatic our world is today and how rapidly it is changing. As one example, I'm calling to you from California, which has not only had the hottest summer on record, but also has the largest fire season on record. And in fact, we are in the middle of fires right now, and the air quality today is very poor because of the smoke from all the fires. In trying to think about how to contribute to reductions of greenhouse gas emissions, we must now also begin to consider how to remove emissions from the air and oceans. And the fundamental math of net zero emissions requires it. In short, any emissions that come from the ground must return to the ground. Any emissions that enter the air must be removed from the air. Otherwise, we will not have net zero. It's kind of that straightforward. In that context, there are many ways to remove CO2 from the air and oceans and to bind it in a durable form for long durations. The group assembled here today represents 4 of those approaches, and I could not ask for a better group of people to discuss this with you today. Let me start by introducing them briefly. Dr. Roger Aines at the Lawrence Livermore National Laboratory, Dr. Lori Guetre at Carbon Engineering, Dr. Tiffany Troxler at Florida State University, and Dr. Yasuhito, Shirato-san. We are going to be hearing from each of them discussing their approach and the way that they think about the problem and challenges of CO2 removal. With that, we will then have a short discussion amongst the panel. We want to leave abundant time for your questions. If you are not familiar with it yet, there is a chat function on the webinar software. You can add questions to the chat function, and we will do our best to include them in our discussions and answer them as they come up. With that, please allow me to introduce the first speaker, Dr. Roger Aines.
Thank you, Julio, and welcome to all of you. I'm going to share my screen now. After we stop emitting all CO2, we're still going to have to remove CO2 from the atmosphere. And how much will we have to remove is shown here in green. The brown is all the emissions that we can get rid of by things like efficiency and carbon capture and storage. And then there will be some residual CO2 that we can't get rid of or that we can't get rid of fast enough. And there are other greenhouse gases like methane that we won't be able to get rid of, so that on the balance, we're going to have to remove by 2050 about 10 billion tons of CO2 per year and more throughout the century. 10 billion tons, by the way, is twice the size of today's oil industry. And there are a number of technologies that we can use for this purpose. We can, of course, use forestry and soil carbon. Bioenergy with carbon capture and storage is a topic that I'm going to talk about now and that you'll hear about more in this meeting. Direct air capture, you're going to hear about also today. All of these are ways that have been developed. They've been, there's some background for them, but none of them are operating at the scale that we need to have them by the mid-century, when we need to be removing billions of tons of CO2. So what are the options that we looked at for California? We said in California, in order to reach net zero, we believe that we're going to need to have about 125 million tons of carbon removal in 2050 in order for the state to achieve net zero emissions. And we added these all up and looked at all the options. And we think that about 25 million tons per year can come from natural solutions, from trees and soil and restoring wetlands. But that's about all we can get from that, because we have never deforested California, and so we can't reforest it. In the middle, you see a big option, 83 million tons per year. We think we can get from taking waste biomass like forestry waste, agricultural waste, trash from cities, and sewage, and grabbing the carbon out of that and putting that carbon permanently underground while we make a fuel or otherwise use energy. But even those two will not be enough on their own. And using as much of them as we possibly can, we still don't get to 125 million tons. And then the remainder, we estimate, at this point, it's really just an estimate, 17 million tons per year would need to be removed by direct air capture. And when we look at the costs of all these, this cost chart shows you what we think the distribution would be. Natural solutions are the least expensive, but we can only get about 25 million tons. In the middle, you see all the orange options are ways to use waste biomass. And what we found was the most efficient way to do that was to convert it into hydrogen. That gets all of the carbon to put underground and generates a valuable fuel, hydrogen, that is now carbon-free. We think those can be done for a cost of about $60 to $70 per ton of CO2 removed, considering selling the hydrogen at the current retail price of about $2 per kilogram. So that's a very effective way to remove CO2 while making hydrogen. Direct air capture we expect to be more expensive at the end, but you can use as much of that as you need to if any of these other options don't come to fruition as fully as we expect them to. And of course, this is just an estimate for all of these. And that range of costs for the total for California would be about $8 billion a year. Depending on the value of the fuels or how much biomass is available, that could vary by about $2 billion per year. So a range between $6 and $10 billion, we think California could achieve enough negative emissions after we've achieved all the emissions reductions that we're capable of doing to get that 125 million tons of negative emissions. Waste biomass will be a very important part of that. It's widely available in California. In the north in red, you see the forestry waste. And of course, a big part of that will be from clearing forests that we need to thin the forest for fire control, which is a very big issue here today. In the center in yellow, you see agricultural waste. That's our Central Valley where much of the United States food is grown. And in blue, you see the trash from the big cities. All of those are good sources of negative emissions when we convert the biomass. And finally, there's a lot of good underground storage in California. Here you see a map of the oil fields in some of the two big oil producing areas in California, and the darkest green areas are the places that are the best for geologic CO2 storage. And we think that California is blessed with terrific geologic storage. Just in these areas that we identified, we found 17 billion tons of safe storage that meets the California regulations, which are the most strict regulations in the world. So in conclusion, we think California can reach carbon neutrality by 2045. Emissions reductions, efficiency, and removal of CO2 will be very important altogether. We're going to need all of this. And the good news is the job and environmental benefits of the new technologies will be substantial. Thank you.
Thank you very much, Roger. That was excellent. A quick comment and question for you. When people often think about bioenergy with CCS, they typically think about fuel crops of some kind, poplar trees or miscanthus grass or something like that. Why the focus on waste?
Many of those crops could potentially conflict with the use of land to make food or other uses for land. And so we chose to first look at the waste material because there is so much waste material that if we could remove 85 million tons, that's a good start. And then we could think about whether we needed those crops later.
Excellent. With that, we turn to Dr. Lori Guetre from Carbon Engineering. Lori, off to you.
Great, thanks so much, Julio, and thanks to ICEF for organizing us and for all of your interest in carbon removal. I work for Carbon Engineering. We're a direct air capture company, and I'm going to share my video. Hi, everyone, and a warm welcome from Vancouver, Canada. Thanks for your time and for your interest in CO2 removal. And many thanks to the Innovation for Cool Earth Forum for the opportunity to talk with you today about direct air capture. Direct air capture is exactly as it sounds, capturing atmospheric CO2 directly from the air. And if that sounds too good to be true, it's important to understand that DAC is not new. We've actually known how to scrub CO2 from the atmosphere for decades, and that's how we put people in spacecraft and submarines. The problem was not that we didn't know how to remove the CO2 from the atmosphere. It was primarily that it was too expensive, costing as much as $1,000 per ton. Traditional scrubbing techniques also face challenges in scaling up from those applications to climate-relevant volumes of CO2. Our founder, David Keith, was an advisor to Bill Gates on climate, and they knew that the world would need a new tool in the toolbox, a technological solution to pull CO2 from the atmosphere at very large scale and at very low cost. And so in 2009, Carbon Engineering was founded to tackle that goal. Fast forward to today, the technology is ready. We've published a detailed techno-economic analysis for our standard commercial DAC plant design that removes 1 million tons of atmospheric CO2 per year, and we're commercializing the technology. The core new technology that we bring is shown in purple here, large-scale DAC at low cost. The question is, how do you put that CO2 to work once you've captured it to make it economic to build this critical infrastructure? It turns out that there are two primary markets for that atmospheric CO2 today. One where you simply sequester that CO2 permanently underground, providing negative emissions to help governments, companies, and individuals decarbonize. The other is to take that atmospheric carbon and combine it with hydrogen to make liquid fuels like diesel and jet fuel. In the fuel synthesis case, you're recycling the carbon in the atmosphere rather than pulling new fossil fuel out of the ground. Carbon Engineering has implemented both of those solutions at our pilot plant in Canada. Key to our large-scale, low-cost solution is that we've used off-the-shelf equipment from other industries in a clever way. We use a non-volatile, non-toxic, closed-loop chemical process that is safe and minimizes operating costs. It's important to note that plants can be located anywhere in the world that has access to air, water, and energy to power the plants. So we have flexibility in where we put these plants, as driven by carbon markets. These plants can also be a tool in addressing climate justice, as they will bring significant economic development and create long-term jobs. The creation of liquid fuels from CO2 is not new, but we chose to implement the fuel synthesis building blocks at our pilot plant in order to demonstrate the process and confirm our economic analysis. So you might ask, if it's possible to create fuel from atmospheric CO2, why isn't anyone already doing that at scale? The answer is that low-cost direct air capture is just one of the required building blocks, and we're seeing a convergence of other innovations and cost down in other key areas, such as the creation of low-cost renewable hydrogen, renewable energy such as wind and solar, and fuel synthesis systems. The outcome is the ability to create ultra-low carbon fuels with atmospheric CO2 that have all of the key advantages that I show on the right. What you also see is a picture of our synthetic fuel, which is the clear liquid on the right, burning alongside traditional fossil diesel on the left. What's valuable about our fuel in the market is what you can't see, the ultra-low carbon intensity. But it's a nice co-benefit for clean air efforts that our synthetic fuel burns cleanly without any of the sulfur and nitrogen oxides and particulates that you typically get when you combust fossil fuels. We get inbound requests from across the globe almost every day by individuals through to large governments asking about net zero. People really want to help. But there's sometimes limited awareness of the size of the problem to get to net zero. So I've included a typical abatement curve, in this case from Goldman Sachs, looking at how much it costs to decarbonize and where we're actually at today. On the x-axis, you'll see the world's current yearly greenhouse gas emissions, 52 billion tons of CO2 equivalent. What jumps out and is noted as number one in purple is the fact that we don't actually have solutions above about 38 gigatons at any cost. So that's a really big problem if we want to get to net zero. Problem number two is that the curve climbs steeply as you approach 38 gigatons to over $1,000 a ton. The third problem is that with a growing population, we're on our way to 80 gigatons a year if we stick to business as usual. And fourth, this only looks at abating today's emissions. It doesn't tackle all of the legacy CO2 molecules floating around in the atmosphere that are already causing climate change. What's clear from this curve is that we need to focus today on accelerating all solutions, DAC and otherwise, that are both affordable and can scale to meet the net zero challenge. The good news is that there is a solution today that can solve the abatement gap, is affordable, has the potential to scale, and supports climate restoration by pulling out that legacy CO2. We know that we can fix this, and we're doing everything we can to move as fast as we can to make this technological solution available to the world at scale. If you could do the end-to-end capture and safe and permanent sequestration of that CO2 for $150 a ton, this is what would happen to the abatement curve. You'd have the option to go all the way to net zero, and you could cap the cost. You'd still need 6% of global GDP, which is a staggering sum, but you'd have net zero in hand, and you could get to work on further reducing the costs for affordable technologies that can scale, like direct air capture. Here's a final look at how we see these solutions rolling out. In 2019, we announced, in cooperation with Oxy Low Carbon Ventures, that we were proceeding with the front-end engineering and design of our first commercial-scale DAC plant in the Permian Basin. We're now over 25,000 person-hours into the design, and you can see a rendering of the plant in the middle. This plant will capture 1 million tons of atmospheric CO2 every year and will be a blueprint for broad plant rollout across the globe. Over the next 10 years, this air treatment infrastructure will get built out in jurisdictions with the strongest policies. By 2050, we see DAC-based solutions playing a significant role in the global effort to achieve net zero, using atmospheric CO2 not only for negative emissions in fuels, but also in many other carbon products. We're excited to be talking with leading companies and governments across the world who are leaning in on climate, wanting to make a difference and help catalyze those solutions to climate change. Finally, there are a bunch of folks around the world working on climate restoration to safe levels like 350 parts per million. At Carbon Engineering, we believe that direct air capture will accelerate our path not only to net zero, but then onward to the important work of climate restoration. That's it. Thanks so much for your time, and to Julio for moderating our panel. I look forward to the discussion.
Thank you so much, Lori. That was superb. Just a quick question here. You mentioned that this project that you have where you're designing that is right now, that you're working with Occidental, you've just begun a new venture, 1.5. If you would take a moment and talk about that, because business innovation is also important.
Great. Okay. Thanks, Julio. Yes. As Julio mentioned, we've actually, it's partners that we've been working with for many years. So we've been working with Oxy, as I mentioned, on this first 1 megaton plant in the Permian Basin for a few years now. We've also had a company called Rasheen Capital Management as an investor in Carbon Engineering. And just a few weeks ago, we announced a partnership with Rasheen and Oxy called a new company called 1.5, who have been formed now to commercialize technology with a focus on the United States and a focus on geologic sequestration. So we're really excited to be working with them. As a direct air capture company, we know how to capture the CO2 at scale, but we need to work with partners around the world that either put that carbon into durable products or put it safely back underground. So we're really excited to be working with 1.5 to do that in the United States.
Excellent, thank you. Whenever I talk about CO2 removal, I make a point of saying that we need to take CO2 out of the air and oceans. And part of that is the work of Dr. Tiffany Troxler at Florida International University. We turn now to her. Tiffany, the stage is yours.
Good morning. My name is Tiffany Troxler, and I'm an associate professor in the Earth and Environment Department at Florida International University, and I'll be speaking to you about coastal blue carbon ecosystems as part of a global portfolio to reach negative emissions. So coastal blue carbon ecosystems, when we talk about coastal blue carbon, we're referring to the vegetated, tidally influenced ecosystems that accumulate carbon. Carbon is buried in situ within soils from the growth and decay of organic matter from plants rooted in the soil, but also can be high in biomass accumulated in forest systems like mangroves. In situ carbon burial in soils differentiates them from other ocean-based photosynthetic organisms like macroalgae of kelp beds and other seaweeds that persist without root systems. In my presentation today, I'll focus on the vegetated ecosystems, which are the mangroves, tidal marshes, and seagrass meadows. So over millennia, coastal wetlands have accumulated or prograded on shorelines around the world with the slow increase in sea level rise. And this progradation has resulted in an accumulation of carbon along these shorelines. For instance, here, we know, in fact, from literature studies that sea level rise drives wetland carbon burial in tidal marshes. On the left, you see the carbon accumulation rate at different wetland sites, tidal wetland sites across the U.S., and on the right, a positive relationship between relative sea level rise and soil accretion rate. And with that increase in soil accretion and progradation of coastal wetlands along shorelines, massive amounts of soil carbon has been accumulated. And with recent estimates showing that mangroves, tidal marshes, and seagrass meadows have sequestered much higher mass of soil carbon as compared to tropical forests, and overall total carbon stocks being higher in these coastal wetland systems than in terrestrial boreal and tropical forests. And we know that plants and the vegetated root systems are most important in the accumulation of this carbon over time. So what we see here is average carbon burial rates for tidal marshes, mangroves, and seagrass meadows, and estimates of their global area to produce estimates of global carbon burial. And this baseline global carbon burial for soil only was estimated at 0.3 to 0.8 gigatons of carbon dioxide per year. And we understand that there is some variation among soil carbon burial rates. And here's an example for a paper published on mangrove forests. And we also understand that while we have this baseline carbon burial, we also have high rates of coastal wetland loss. And simply from halting the conversion of coastal wetlands to other land uses could avoid up to 1 gigaton of carbon dioxide per year globally. Given the research that had been developed up until that time, the IPCC took some work to develop methodological guidelines to include wetlands in National Greenhouse Gas Inventory guidelines, and coastal wetlands were among those. And later, as part of a National Academy's report, coastal blue carbon was considered among approaches as a negative emissions technology. And here, coastal blue carbon approaches being practices that increase the amount of carbon stored in living plants or soils in tidal marshes, mangroves, and seagrass meadows. And that research agenda identified 5 management practices in different phases of readiness to increase carbon dioxide removal, which included active ecosystem management, restoration and creation of coastal blue carbon ecosystems, nature-based adaptation approaches, managed wetland transgression, and projects that included augmentation with carbon-rich materials. And a conclusion of the of the study was that while coastal blue carbon ecosystems are cover relatively smaller areas than some of the other natural approaches, because the cost of carbon removal can be minimized if these projects are done to target other benefits such as coastal ecosystem services and coastal adaptation, that the cost of the carbon is low to zero. And so some of the cumulative potential carbon sequestration capacity estimates that were developed put coastal blue carbon ecosystems being able to implement each of the approaches reviewed could potentially result in 5 gigatons of carbon dioxide removal by 2100. And when you consider this at a global level, we're looking at 6 to 40 gigatons of carbon dioxide that could be sequestered globally, just based on the area of ecosystems that we've lost in the last 40 years. There are a number of key challenges in reaching this potential. One is permanence, understanding the extent to which the carbon that's buried will, over what time frame that carbon will remain buried. Coastal management is often something that's difficult to control, so having a system in place where coastal management regimes can promote carbon burial and permanence. And then other greenhouse gases, so understanding the variation in methane, which we know is very low emissions once you reach a certain salinity threshold, and then the potential amplification of methane with increase in carbon dioxide with climate change. So these challenges can be addressed with more demonstration and deployment projects and improved and expanded monitoring. Thank you very much.
I would ask you to just take a second and make a differentiation between sort of wetland restoration versus these sort of other approaches which you've talked about, say seagrasses and mangroves. And thinking about this not so much from a scientific perspective, but from an operational perspective.
Yes, in the context of challenges with those different coastal ecosystem types, we have less information about the coverage of historical seagrass beds, and there are a number of other coastal management issues to address to try to reach what could be the potentials of seagrass meadow restoration, but I think it's an active area of understanding where those meadows can achieve those carbon accumulation rates that would be expected, and those coastal ecosystems along shorelines pose another set of challenges, but we have a better understanding of how we can achieve those potentials in those types of systems.
Thank you. That's very helpful. Last, but by no means least, we are pleased to have Shirato-san, Dr. Yasuhito Shirato from the Institute for Agro-Environmental Sciences at NERO. Thank you so much for joining us to talk about soil carbon.
Hello, everybody. I'm Yasuhito Shirato from Institute for Agro-Environmental Sciences, NARO, National Agriculture and Food Research Organization, Japan. My talk today is about soil carbon sequestration for climate change mitigation and food security. This photo is soil profile of 1 meter depth. Here is soil surface, and here is 1 meter below ground. Carbon is accumulated here as dark colored soil organic matter. And this soil organic matter is important index of soil productivity. Carbon is cycling among 3 carbon pools: atmosphere, biomass, and soil. And soil is the biggest carbon pool among these 3. Storing carbon in soils has huge potential to mitigate increase in atmospheric CO2 and contribute to sustainable food production. The 4-per-meal initiative, launched in 2015 at Paris during COP21, it highlights the role of soil organic matter for food security, adaptation to climate change, and mitigation of greenhouse gas emission. This is global carbon cycle at present, A, and in the future, B and C. At present, atmospheric CO2 increase 4.3 gigaton annually, and it is projected to be 6.1 in the future of business as usual. But if the 4-per-meal target will be achieved, it will be 0. By increasing the amount of topsoil carbon 3.7 gigaton annually. The amount of carbon in topsoil 40 centimeter is 860 gigaton. So this 3.7 divided by 860 is 4-per-meal. Thus, storing carbon in soils and increasing soil carbon pool can contribute to climate change mitigation. This figure shows that the soil carbon and crop yield have positive correlation. This is just an example, but generally, soils with higher soil organic matter have higher productivity. The amount of soil carbon is therefore one of the indicators of soil productivity. So, increasing soil carbon in soil is effective both for climate change mitigation and food security. An example of management option to increase soil carbon is to increase carbon input to soils. This figure shows that increase carbon input to soils by adding organic manure is effective in increasing soil carbon. Based on the data from long-term field experiment, increasing return of crop residue is also effective. It is important to return crop residue as much as possible. The use of cover crop or green manure is effective too. Crops with big below-ground parts is good because the below-ground parts enter soils automatically. Another management option is to reduce decomposition of soil carbon. No tillage or reduced tillage. is one of a promising technique to reduce soil organic matter decomposition. This figure shows that the soils from no-till plot has higher soil carbon compared to tillage plot, especially in the near surface part, 1, 3, or 5 centimeter depth. I want to emphasize that these soil management options are not high-tech, not difficult technically. So implementation of low-tech traditional agronomic management practices in a wider area is a challenge. It needs policy intervention, for example, a subsidy program, and carbon offset trading system is effective also. So we should highlight a co-benefit of these management practices. For example, adaptation, productivity, or profitability for producers. So to help producers' decision making by visualization of the effects of these management practices are important. This is a web-based decision support tool which we developed in Japan. The user can calculate easily the changes in soil carbon and other greenhouse gas emissions very easily by a very easy interface. Mechanistic models are running behind, and a similar tool called Comet Farm was developed in the US. I believe this kind of decision support tools are useful for producers or policymakers to support their decision to change their agricultural management practices in a sustainable way. This is a preliminary result of survey on NDCs done by the 4-Pamir initiative. At present, only 13 countries include soil carbon in their NDC as emission reduction target of countries. Finally, I'd like to mention that sustainable soil management to store carbon in soils can contribute to many of SDGs. Similarly, it contributes not only UNFCCC to combat climate change, but also to the UNCCD to combat desertification and land degradation, and also to CBD to combat loss of biodiversity. I wanted to tell you that the importance of sustainable soil management and its huge potential in this presentation. Thank you for your attention.
Thank you, Shirato-san, very much for your presentation. A question for you about the monitoring of soil carbon. As you know, this is challenging, and there are many groups out there trying to understand how best to do that in order to monetize the soil carbon. Can you talk just for a moment on what's the state of the art of soil carbon monitoring today and what we need from a research perspective?
Okay, thank you, Julio. It's a good question. The monitoring soil carbon takes time. So we need to conduct long-term field monitoring. So a lot of countries has already have long-term field experiment with different set of management practices. But a Western country like Europe or the US, they have a lot of data. But for example, Asian country or the African country, still we don't have enough data. So, but if we start the experiment now, we need time to get long-term data. So I hope immediately a lot of countries will start that kind of monitoring project.
Indeed, that is a priority that was identified by the national academies, as Tiffany mentioned. It is also something to consider for mission innovation, and an innovation agenda around soil carbon as one topic. I want to take a few minutes now and ask some questions of the entire panel, because there are some cross-cutting themes and questions to consider. After about 10 minutes, I plan to open up to questions from the audience, and we will have 20 minutes to discuss your questions. But let me start by saying that I wish we were all together in Japan right now. I wish we were in the Hotel Chinzanso, which I very much like. I'd look forward to doing that next year, God be willing, at ICEF. Let me first ask about the role of policy. All of you have mentioned the need for policy interventions of some kind. They're all quite different. What I want to ask you is how you think that policy can support the development of projects and standards that are so important to for financing. Why don't we start with you, Roger, and then anyone who wants to come in after that.
I think one of the great challenges in the financing and policy for negative emissions is that we're fundamentally taking out the trash. We're not making a new product. In some cases, we're making things better. We're making soil better. We're making our oceans better. But we're not selling a product. And so the policies have to provide monetary support for the actual technology. In California, we have the low carbon fuel standard, which today includes direct air capture as one of the things that it pays for. And that at $200 a ton is the highest amount of money that's available in the world for policy support. But we need a lot more of those, I think, to make these technologies business ready. And I like to say that when you do billions of tons of anything, you need businesses that make money doing it.
Others who want to add to that discussion?
Just echo what Roger said. It's policies that are, I've never talked about policies that are for taking out the garbage, but that's absolutely right. And unfortunately, CO2 molecules are invisible floating around us. And so, you know, it's only with growing awareness of the need to tackle climate change that we're starting to see these strong policies emerge. But it's really exciting to have low carbon fuel standards like California's leadership, as well as carbon policies rolling out across the world that are putting a value on carbon removal that are at a high enough price tag to start to really accelerate these technological solutions. So that's exciting. But I would say also just as exciting is the new participation by voluntary participants, by companies that are announcing really big dollars being spent voluntarily in advance of any kind of regulation to take out that carbon garbage, trying to say, look, we need to accelerate and we can help in the short term while those policies come online. So excited to see governments and policy development all across the world that is recognizing this and putting a price on carbon, but also those voluntary markets. Really excited.
Yeah,
Excellent.
Julio, if I could just offer also, I would say that the policy absolutely has to be based on the best available science so that we can ensure that we're getting the carbon removal that we're financing. And you know, some of the best policy out there is exactly that. So we need to continue to push on the sufficient science to help support that.
Indeed, we do. And following sort of Lori's thinking, a lot of the recent interest in CO2 removal and negative emissions comes from the arithmetic of net zero. That as countries begin to make net zero pledges, as companies begin to make net zero pledges, they realize how much CO2 removal that means and how hard it is. In that context, I want to ask you all a question about scale. Roger made this point with his presentation that right now We simply don't have these technologies deployed at scale. We know we have to get to an enormous global industry in the next 30 years. So the question is, what's the next step? What's the most important increment to get from where we are today to a gigaton in each of your areas? Don't be shy.
I'll go first. The plant that's in behind me and that was in our video, Carbon Engineering is focused on a 1 megaton building block as its target commercial plant ever since we were founded. And how do we do it at climate relevant scale? So we'll have a 1 megaton building block. To get to 1 gigaton, we need 1,000 of these. And so what we need is to get there is the growth of those markets to let us accelerate. We know how to build this clean infrastructure. We have partners who can put it back underground safely or turn it into carbon products. What we just need is the aggregation of that market demand to pull this through as fast as we can.
The aggregation of that market demand at the price you need.
Absolutely.
Dr. Shirato, if I may, what's necessary from your perspective? What's the next step to get towards a gigaton?
Okay. Each of individual farmers' activity will make very small contribution, but the total of soil carbon, the amount of total soil carbon is huge, as I presented. So the implementation to the wider area of the world is important. And policy intervention is very important. But as I mentioned, this soil carbon sequestration has co-benefit. It can contribute to better production. So this can be an incentive for farmers. So for starting, the policy intervention is needed, but after that, if they know that their activity to sequester carbon is also good for their productivity, automatically it will be automatically go for the big area. So co-benefit is the one key word, I think. I don't know if I could answer your question.
That's quite okay. I liked your answer very much. Anything from Roger or Tiffany? And then we'll turn to the questions we've received from the audience.
I just want to say that it's in the early days here, it's very important to get more projects on the ground because we need to learn. The typical learning rate in technology is based upon doubling of the number of units that you make. So every time you double the number of units, you learn by a certain amount and the cost comes down. And an average number for that in renewable energy is about 15%. So if we build 2 units, the price drops by 15%. We build 4 more units, the price drops by another 15%. It's those early units that require government support, and that's where policy support has to happen. This is not going to be commercial right now. That there needs to be money put on the table to get those early plants built so that the price can come down.
So for you, the most important next steps are actually an innovation agenda around demonstration and deployment.
Absolutely.
Tiffany, last shot.
Yeah, I can't help but like to echo both what Shirato-san has said as well as Dr. Aines. Those equally apply to coastal blue carbon. Thank you.
Excellent. We've already got some questions from the audience. I will use my prerogative here to direct them to various members of the panel. The first is a question about direct air capture. I'm going to send this to both Lori and to Roger. It says nuclear seems to be the energy source used for direct air capture. Is that correct?
I'll answer from a sort of an implementation perspective that we look to the standards, the policies that are set for what's required of us, whether it's putting the CO2 back underground safely, the permanence requirements, or the energy sources that we can use to power the plants. There are certainly policies that either have or are contemplating wind, solar, hydro, nuclear as clean energy sources, and where those policies allow for nuclear, it's a great fit. So yeah, so we look to the policies and what they require in terms of the kinds of energy we can use.
Roger, anything to add?
One of the challenges, you might think that we could use our existing nuclear plants to use the heat, which is what you need for direct air capture. But unfortunately, that means that you have to build the capture facility right next to the nuclear plant. And to match the power of a nuclear plant, you'd need about 20 square kilometers of capture devices like the one that is behind Lori. And often that space is not available. And that space turns out to be a big limitation in many of the things that we want to do. We're not limited as much by land, as much by money as we are by land.
Let me just add something briefly to that. The energy requirements for most direct air capture systems are about 4 parts heat, 1 part electricity. What is true for all of them is that in order to have a positive climate benefit, those energy inputs need to have a very low carbon footprint. So nuclear is possible, so is solar, so is wind, so is hydro, so is geothermal. But those trade-offs that Roger mentioned about land and access and these sorts of things become important. The next question is, what price would be acceptable as a carbon price for carbon removal? I'm going to give that to everybody, but why don't I start with Tiffany and then Yasuhito. Tiffany, you first. What's an acceptable price for carbon removal?
That's an interesting question. What I'm struck by learning more about the engineered approaches is the exponential increase in the value of the carbon over time as our climate change mitigation problem becomes extreme. And so I'd have to say it's dependent on our demand.
That's a very good answer. Shirato-san, do you have anything to add?
Yes, the price to cover the additional cost of the additional management practices. But most of management practices have co-benefit, as I mentioned. So if such management can increase yield, it can cover the increase in income, can cover the cost. And if not, the policy subsidy program, like such kind of policy intervention can help, or credit offset carbon credit system can help them. Yeah, so anyway, the cost is very cheap compared to other measures. So agricultural practice are the most very cheap. Yeah.
Roger, Lori, anything to add?
I'll put a number on it. I think that a country or a large corporation that was looking to have a portfolio of solutions that included all of the kinds of things that we've talked about, which I think is a good idea, by the way, that portfolio is probably going to cost them about $100 a ton on average. There will be many less expensive options, and there will be some that are much more expensive. But that number, $100, is the number that I think you should have in mind when you think about this kind of worldwide approach at billions of tons.
I think that's a very provocative and excellent answer, too. Since we know we need all of these pathways, and they all have different price points, and all of them are tiny and all need to be large, we need more money in all of them. And right now, the task is scaling. The task is not optimization of cost. And so building a portfolio that has many elements is a good thing to do. we are seeing that coming out of the voluntary market now. We are seeing companies like Microsoft and Amazon and other companies developing a portfolio that includes high cost and low cost options in order to get the market scaled. The next question we have is, how should we reflect direct air capture and storage conducted outside our country into the National Emission Registry? This one's to you, Lori. It's really a governance question, but a good one.
Yeah, it's a great question. And absolutely, it's a governance question. I guess one of the interesting things to look at is the California Low Carbon Fuel Standard and how they've set their policy for direct air capture and sequestration. And under the California LCFS, because the atmosphere is a shared resource across the world, in fact, a ton of atmospheric CO2 that is captured and permanently stored, permanently sequestered, could count toward the California LCFS if that project was done anywhere in the world. And so I think that's sort of a great leadership way to look at that shared resource. It's very important as we unambiguously capture and sequester and track the life cycle analysis of that captured CO2, that the environmental benefit is retired only once, that it's only credited once. But absolutely, you could look at captured atmospheric CO2 sequestered happening elsewhere in the world and counting toward the National Emission Registry for or national contribution by a country if they've put the funds toward doing that project and counted the environmental benefit.
Mm-hmm. Right. This is fundamentally the province of lawyers and diplomats. I think I'm the closest thing on this panel to those things, so let me try to answer from my experience. The key element is the one Lori already said: you only get to count it once. And so who gets to count it is really a function of contract. If Japan contracted a direct air capture project in Alaska, Japan gets to count it if they pay for it. And I think that that's a reasonable way of thinking about it. When we think about CO2 removal as a whole, not just in direct air capture, it's a little different, because then there are potential risks associated with something we call eco-colonialism, in which a rich country basically harvests biomass in a poor country, and the poor country does not get the carbon benefit or the economic benefit. And as we think about this as a global problem, these questions will come up and we have to think carefully and well about them. I hope that in future ICEF meetings, that the sociology of these issues will also be discussed. The next question: is there a way to accelerate CO2 removal by wetlands? And here I'm going to turn that over to Tiffany, who has the deepest understanding.
Thank you, Julio. Yeah, we need to identify areas where wetlands can be restored and created. And one of the opportunities that we identified in the National Academy's report is through climate adaptation. We have a number of initiatives in which what's called nature-based climate adaptation is being pursued in some areas more aggressively than others. And those also provide economic opportunities, both for the engineering companies that are pursuing those projects, but also for the damages avoided associated with the climate adaptation benefit of revegetating or restoring shorelines where they've been hardened or developed.
Thank you. That same concept about preserving and restoring wetlands also applies to soils. We have lost a lot of soil carbon, and so we can restore soil carbon that has been lost and preserve good soil carbon stocks. It also applies to forests. There are places in the world where we have lost forests and could restore them. I'm going to come back to that a bit at the end, but we have a few more questions still and another 10 minutes to go. So let me start by asking, this is for Dr. Shirato, how could you verify carbon reductions in soil management? What are the technologies and approaches to validate and verify soil carbon reduction?
Okay. Traditionally, we conduct field experiments and take soil sample and analyze in the laboratory. But as I shown today, we already have a lot of data, lot of facts to show that some of management can have positive effect on soil carbon. So by gathering these data, we soil science community have developed models to calculate. So with that model, we can relate the activity, the management to the result of soil carbon. And also, as I show you today, by using such models, mechanistic models, we have developed some decision support tool to if the producers enter his condition, his location, and his management practices, it's very easy to calculate what will be happening. So basically, we need monitoring, but we already have model to calculate it.
Thank you. And actually, in thinking about soil carbon monitoring, what's increasingly clear is that we need a combination of modeling, direct sampling, and remote sensing. And as these things come together, we're getting better and getting more precise. As we are getting more accurate and more precise, we are also reducing the costs. Today, the cost of soil monitoring is actually very expensive, but we believe these techniques together can reduce the cost and hopefully quickly. Again, that's another good innovation agenda. The last question we have here is how do you, and this is for everyone, how do you think removal investment should be managed with energy tariffs towards sustainable development? So for example, should we consider some kind of surcharge in energy development and, or delivery that could be applied to CO2 removal?
Go first. I think energy delivery, we often think of that as electricity, and electricity really should be dealt with by reducing the emissions at the source. And it's probably not a good topic for carbon dioxide removal as a way to balance those emissions, because those large point sources can be dealt with at the source, and then that can be dealt with in fairly direct, straightforward policy measures. So I think it's really the things on the periphery, the emissions from ruminant animals, the small amounts of internal combustion engines that we can't get rid of, farm emissions, nitrous oxide, things like that, that carbon dioxide removal really makes up for. And there, it's very hard to track that because they are all very small emissions and there's just a lot of them.
One of the things that is also true is that the politics of energy surcharges are complicated. And we learned that most dramatically, I think, with the Yellow Vest protests in France, in which a fairly modest carbon tax on gasoline almost brought down the French government. And we've seen these things in other, we've seen the same thing in Australia. We almost saw this in Canada. I think economic optimization would suggest carbon prices. Political optimization suggests something else. And I towards that end, I'm not committed to any one policy approach. I think different countries and different jurisdictions can choose different ways to do this. What is true is we are simply not doing enough today. We certainly need to gather more money and we need to spend it on this topic. So however that is gathered and however that is spent, as long as it is just and fair, I'm in favor of it. And after that, reasonable people can disagree. Laura, you wanted to add to that?
Maybe I'll hop in a little bit more with the voluntary participation as opposed to a government energy tariff. And you know, one of the great things, as Roger says, if we look at the kinds of areas where it's hard to decarbonize, transportation is one. And so if we look at how voluntary markets are helping to facilitate this, we're really excited by the fact that rideshare companies are starting to offer up to their customers the ability to go green and hail a hybrid vehicle or a low emissions vehicle. And consumers are paying, an extra $1 in order to have a rideshare in a green vehicle. So it's not a tariff, it's a voluntary participation, but it's helping to decarbonize transportation. And of course, you can remove the CO2 that came from the emissions from the use of liquid fuels as well. So it's a way of engaging. I think as we engage more the public who are very much wanting to do something about climate change in ways that allow them to directly participate, it's pretty exciting to see that happening in parallel with the regulated market.
Thank you. The opposite of a voluntary market is a compliance market. Many people here, I'm sure, are familiar with the European Trading Scheme, the ETS, and there has been an enormous political uproar around the idea of using public funds and the ETS to contribute to a CO2 removal strategy. And Frans Timmermans at the EU is dealing with that in real time. There's another way to think about a compliance market too, which is around something like an emission standard. So the United States has proposed a law, and California has adopted a law, which is a 100% zero carbon electricity standard. And to Roger's point, it may be that the last 5% of that is very hard to get, in which case people can just pay for direct air capture or soil carbon as a compliance option. And that would need to be set by standards of various kinds. Creating those standards is another policy imperative which we need to take on. This actually is going to lead me to my closing comment because we're very close to time. I recently wrote a paper on engineered pathways to CO2 removal, and in it I made the case that we need to be humble about what we know. Most of us are comfortable thinking about what we know and what we don't know from a technical perspective. A scientist has a good understanding of what they really understand and what they don't quite understand and what they really don't understand. Most of them, however, don't think enough about the fact that they know almost nothing about politics. They know almost nothing about finance. They know almost nothing about public opinion. They know almost nothing about markets. And in fact, as we deploy the CO2 removal technologies we're discussing here today, it will enter these other domains. It will enter the domain of politics and business and markets and finance and public opinion. And towards that end, I think we have to be humble about how hard this will be and how long it will take. That humility must also match the ambition that we have and that we must urgently scale up these solutions. In that exact context, I am grateful for all of our discussants today. Thank you again to Dr. Guetre, Dr. Aines, Dr. Shirato, and Dr. Troxler. And thank you all for being here. And one final thanks to ICEF for hosting this workshop. Thank you all.